Olá! A IUPAP, International Union for Pure and Applied Physics, está interessada em muitas coisas. Dentre elas, a definição das unidades básicas que nós usamos no dia a dia, a manutenção das constantes fundamentais, mas também está muito interessada nos desafios que a ciência tem atualmente. Na área da física são muitos os desafios. Nós temos desafios desde o entendimento das partículas elementares, da matéria condensada, na física nuclear, na biofísica, na astrofísica. Em todas as áreas, ou sub-áreas da física, nós temos desafios. Para que você saiba quais são esses desafios, a IUPAP organizou um workshop especial, que chama-se Entendendo os Desafios da Física Moderna. Cada área da física está aqui sendo apresentada por um líder, membro da IUPAP, e que você terá então agora a chance de entender, através desta apresentação, os desafios que a área apresenta e como os físicos, de um modo geral, estão superando esses desafios para que a física seja um instrumento de entendimento das ciências naturais e que auxilie o homem não apenas a avançar o seu conhecimento, mas a tornar a ciência um instrumento útil da melhoria de vida de cada um existente nesse planeta e nesse universo. Assista e também faça parte do entendimento dos desafios da física moderna. Boa sorte!
Well, we begin this last session for today with low temperature physics. John Saunders.
So we in C5 are currently writing a fairly comprehensive summary of LT28. That's our major triennial meeting. That will appear in the conference proceedings. So I hope you forgive me that for now I'm just going to give some kind of overview of my own interests with some context. So we go about low temperature physics in a different way from the cold atoms community. We have a different set of toys. You can see one of them here. This is a dilution refrigerator with a nuclear adiabatic demagnetization stage hanging off the end. And it's able to cool anything down in principle to about 100 microkelvin. So you could give me something that you would like to cool down, and I could try. Certainly the platform is there. It's about thermalizing the object that you wish to cool to that platform, but it has that flexibility. And we also have a lot of flexibility in the instrumentation that we can use. So what kind of quantum systems, and by that I mean materials and devices, are we going to explore, and why is this of any interest? So when I was, I guess, in my mid-teens, this book by George Gamow is the one that first introduced me to the concept of temperature. And shortly after that, I read this amazing book. You see it's 12 shillings and sixpence. That's my copy. Quest for Absolute Zero. And this is our version of history. As Winston Churchill told us, if you want to secure your place in history, then make sure you write it yourself. So this is our tribe's version of the history of low temperature physics. You can see outer space at 3 Kelvin, and here we are. We've cooled superfluid helium-4 into both Einstein condensate, or this system is strongly interacting. And we've managed to also cool helium-3 to way below 1 millikelvin, where it goes superfluid. More of it anon. So taken from this book is a history of the lowest temperatures that man has achieved as a function of time. In the 19th century, they were very keen, and there was a lot of excitement about liquefying gases. And then each change in the derivative here has got to do with the invention of a new cooling technology. And you can see with magnetic refrigeration, we kind of ran out of steam at about 1 microkelvin, which is the coldest that a piece of copper has been called. And here's the new kids on the block, as it were, the laser cooling of atoms. But it isn't about achieving record low temperatures, it's about the fundamental physics that you can do at sufficiently low temperatures. So what kinds of things are we interested in? Well, quantum materials, and here are 5 classes of quantum materials I'm going to briefly refer to. Something that's huge in this field is engineered quantum objects, so that a superconducting loop will behave effectively as a giant atom, an artificial atom. It has a coherent state, and that's the basis of superconducting qubits. And now there's a lot of interest also in arrays of artificial atoms. Also mechanical systems. So I'm not really going to talk very much about this, although it is huge in our field. And the other thing we must be conscious of is nurturing and developing any kind of experimental capability. Because if you have a gap, a generational gap, then you can completely lose the ability to do certain highly technical tasks. So there's a good new younger generation coming into the field, these are the issues that are important. As I think I said, nuclear adiabatic demagnetization is the method of choice for cooling to about 100 microkelvin. And I think what we've made some advances in recently is controlling the external heat leaks that limit how cold you can make a sample. We also need to work hard in developing measurement techniques that dissipate very low levels of energy. And we have to be able to measure the temperature. So, as you know, and you heard earlier, there's been essentially a revolution in condensed matter physics over the last 10 years or so, with the recognition that the topology of systems is hugely important. So whereas previously phase transitions were about just breaking symmetry, now it's realized that the topology of the system is essential, and Thouless and co-workers first really came up with this idea in the context of the quantum Hall effect, hence the Nobel Prize in 2016, sorry. You heard a little bit earlier about topological insulators, materials where the bulk of the system is an insulator, but because of the topology of the band structure of the material, there are excitations that live on the surface that are conducting. And this is the idea of bulk-edge correspondence, the idea that the topology of the bulk of the material governs the properties of the surfaces or edges. In the case of the quantum Hall effect, it's the edge. So until very recently, there wasn't any convincing example of a topological superconductor. There's been recent work on copper-insulated bismuth selenide. Our argument is that superfluid helium-3 is a known topological system, and so it is clearly analogous, as I will try to explain in a moment, to topological superconductors. It's neutral, but that's handy. And it has different phases, which I'll talk about now. Just let's look at this phase diagram. Helium-3 remains liquid down to the absolute zero of temperature. That's a consequence of weak binding and the Heisenberg uncertainty principle. And in the pressure temperature plane, here we have the normal state, and there are transitions into two distinct superfluid phases, the A phase and the B phase. And they differ in the symmetry of the gap. This has a uniform gap. This has a node at the north pole and the south pole, and the details of the order parameter. The discovery of these phases was made by these three gentlemen. I had the privilege of working under Bob Richardson. That was my first postdoc, an absolutely inspirational scientist, and explained by Tony Leggett, who got the prize in 2003. So the difference between superfluid helium-3 and conventional superconductors, as explained in BCS theory, is the pairs form with 1 unit of orbital angular momentum. And then because of the Pauli exclusion principle, they're in a spin triplet state, as hopefully you can see from these wave functions. And thinking heuristically of the pair as a kind of diatomic molecule, the pairs form at the Fermi surface, and this energy gap is very much less than the Fermi energy. Anyway, the size of those pairs is tunable by pressure, but at zero pressure it's about 100 nanometers. Now, the recognition that this system was important topologically is due to Wolovic. Anyone who wants to learn more about superfluid helium-3 should read these 3 books. And the beauty of it is that there are 2 phases. The A phase is chiral, so I think you can see that all the pairs form in a triplet state. You only have up and down components of the spin. And all the pairs form with their orbital angular momentum, which is 1, pointing in the same direction. Whereas in the B phase, there's strong spin-orbit coupling between the spin of the pairs and the projection of their orbital angular momentum. They form in a state with total angular momentum equal to 0. And this state is time reversal invariant. So these have quite different topological properties. So just a brief slide for your amusement. Grisha Wolovic, who's probably the leading theorist in this field, has a view that the universe is the universe of science. These are all interesting topics in science. Is one where helium-3 sits very much at the center of that universe. So I've called it the Wolovician universe. It's like a change of perspective. It's worth thinking about. It really does have a remarkable. It's really a remarkable laboratory with analogs across the whole spectrum of physics. The new experimental direction that we're exploring is to take superfluid helium-3 and to confine it on the nanoscale. So if you're confined in a very thin, yellow is superfluid helium-3, it's in a very thin cavity. So clearly the surfaces and edges are going to play a very, very important role. And if the essence of a topological system is bulk edge correspondence, then this is a good playground. So what we find is that the confinement dramatically alters the phase diagram. You can see in bulk the A phase is just up here, but under confinement we can stabilize the A phase down here. And if what we're interested in is edges and interfaces, then just imagine this. If confinement is our control parameter, then we can engineer a nanostructure in which the height of the nanostructure varies, such that here, where the height is small, the superfluid will not be able to form, whereas here, there is superfluid. So we can create very clean interfaces within the same material, within liquid helium-3, between entirely new states of matter. So the helium-3 material, as it were, is determined by confinement. So this reminds me a little bit of the p-n junction in silicon, in that you can have a very clean junction within a single material. Here's a cartoon of the B phase, where this hedgehog structure, the message there is that it is strongly spin-orbit coupled. This is the energy gap of the superfluid helium-3 B phase. And because of bulk edge correspondence, there is this dispersion of surface excitations that lie in the middle of the gap. And these are helical. The orientation of the spin is correlated with the direction of the momentum. And they are essentially Majorana fermions that are existing on the surface. So experiments to measure and detect those are something that are important to us. This year's Nobel Prize was about the Koslitz-Seldes transition. I guess the paradigm for that is the superfluid transition in an atomically thin helium-4 film. In 1939, it was known that a bucket of helium-4 would empty because of film flow. It wasn't until 1978 that it was realized that the phase transition in an atomically thin helium-4 film is governed by the vortex-anti-vortex unbinding transition. And these are the real and imaginary parts of the response function described by time-dependent Koslitz-Seldes theory. And what we would like to do is to see what happens when we replace the thin helium-4 film by helium-3 film. And there are different regimes because whereas in helium-4 the coherence length is on the order of an interatomic spacing, as I think I said a moment ago, the coherence length in superfluid helium-3 is the Cooper pair diameter, which can be as large as 100 nanometers. So there are these various different regimes, and the complicated symmetry of the superfluid helium-3 phases will lead to more interesting class of two-dimensional phase transitions, basically because the topological defects in superfluid helium-3 are more complex than the simple vortices that exist in superfluid helium-4. So now I'm going to change gear and talk about superconductors. An idea that arose in the late 90s, this is work from Lonserich's group in Cambridge, is that you can, at low temperatures, drive a phase transition between two states. And here this is an antiferromagnetic state, and here this is a non-magnetic state. And at the t=0 phase transition between these magnetically ordered and magnetically disordered, superconductivity appears. So the idea is that quantum fluctuations at that quantum critical point are responsible for the superconductivity, and this is an idea that also plays out in high TC. And so we've been recently working on this material, ytterbium rhodium-2, silicon-2. In this case, what you do is the control parameter that drives the system from one phase to another is magnetic field. And what you can see is this Dutch orange region, which indicates a typhoon of anomalous transport that's associated with this quantum critical point. And the $64,000 question in this system is, where is the superconducting phase that's seen in the cerium-based materials? And in this paper, there is no evidence, well, actually, it hasn't been studied out at this field, but what happened was that they saw superconductivity at low magnetic fields. Now, these are very low temperatures of 2 millikelvin, and what's being used here is the magnetic signal of the phase transition. So what you'd like to do is the Camerlinghonis experiment to see the resistive transition to superconductivity. And this is what we see in this material. And in order to do low dissipation measurements, rather than doing Ohm's law, we use the fluctuation dissipation theorem and measure the noise. And if we measure the noise, which we can do with this setup, so the Johnson noise voltage across this resistor then drives the current through this loop, which is sensed by the squid. So a squid is essentially a very sensitive current amplifier. And so in this measurement, we can measure both the temperature and the resistance of the sample. We see this very strange transition, which I believe is intrinsic behavior, although that needs more work. And then as a function of magnetic field, the transition to superconductivity has this peculiar shape. And what this is telling us is that the nuclear magnetism is also playing a role. The thing about ytterbium is it has a huge hyperfine coupling constant. So the relevant magnetism is not simply the electronic magnetism, but that of the electronic magnetism coupled with the nucleus. And the beauty of ytterbium is that it has several isotopes which all have different magnetic properties. In particular, ytterbium-174 is non-magnetic. So we can, as it were, tune the magnetism of this system by changing the ytterbium isotope, which I think is kind of neat. As somebody who works on helium-3 and helium-4, the idea of seeing different physics with different isotopes is attractive. So there are other systems that you can look at. The quantum spin liquid is a state which theorists dream up these exotic ground states of matter, and then the question is to find a realization of that state of matter in nature. And that's often a challenge. There are plenty of candidates for quantum spin liquids, but after a while, it turns out that there are features of them which demonstrate that they aren't quantum spin liquids. So a quantum spin liquid is a system of spins that does not order at t equals 0 in a nutshell. And we can study that in two-dimensional helium. And here's an example of a mass diverging Mott transition in two-dimensional helium-3. So the idea is then that the Mott insulator has frustrated spin exchange. So you can write the spin exchange Hamiltonian in terms of permutation operators. This idea is also due to Thouless. This cycle is antiferromagnetic. This one is ferromagnetic. So you have frustration both from the triangular geometry of the lattice, but also because of these competing ring exchange cycles. And you're also near to a Mott insulator transition. And those are the conditions that you need to see quantum spin liquid behavior. So the other thing that we're interested in is cooling other kinds of condensed matter systems down. So this is the well-known two-dimensional electron gas formed in a gallium arsenide heterostructure. And it's been a challenge for many years to actually cool this down into the sub-millikelvin regime. And the motivation for this is that there are exotic fractional quantum Hall effect states, particularly the 5-half state, which corresponds to some pairing of composite fermions, which isn't very well understood. And then there are also nanoelectronic devices that you can fabricate by gating the two-dimensional electron gas. So you can deplete here and here, form a quantum wire, and in that quantum wire it's predicted that the electrons will spin order, and then you can imagine having some spintronic device. So after a lot of effort, we've managed to cool these two-dimensional electron gases down to 1 millikelvin. It requires understanding the thermalization by building such a thermal model. But what I want to draw your attention to is that the heat leaks to this sample, which measure a few millimeters by a few millimeters, are as low as a few femtowatts. And that's the key to cooling these systems down. I'm going to skip that. So this is what the cooling platforms look like. This is the nuclear demagnetization stage. This cryostat is targeted at cooling solid state systems like the ytterbium rhodium-2 silicon-2 and the 2-deg to below 1 millikelvin. And we have other demag systems for looking at, here's the topological superfluid helium-3 in a nanostructure. And another important piece of technology is to make this ultra-low temperature, these ultra-low temperature platforms available to a wider community. That means looking at the possibility of using cryogen-free dilution refrigerators. And so we've made a proof of principle cryostat to do that. So this doesn't use liquid helium. You don't need to have a helium liquefier to produce temperatures below 1 millikelvin. And at the moment, we're moving from a proof of principle to a full-scale prototype with Oxford Instruments. So I'd like to end with a few words on collaboration and organization. Here we are, little old Royal Holloway, University of London, on the edge of, on the western edge of London, close to Heathrow Airport. This is our Victorian founders building. Our lab is over here somewhere. And so it's very, very important to collaborate, and the vehicle for collaboration and maximizing the scientific impact of our research and its technological development is the European microkelvin platform. So we believe, we argue that ultra-low temperatures are important for a diverse spectrum of fields. You can just glance at the titles there. So the way that this is done then is we have a virtual laboratory. So these yellow dots are different labs across Europe. We had some European Union consortium funding, and we're about to apply for some more. And the idea then is to provide ultra-low temperature platforms for users across Europe and across the world to run experiments, because this kind of technical capability is not widely shared. So I just want to end now, as one does, with the list of, these are our international collaborators. This is where our support comes from. This is a brief summary of what we're doing. And last but not least, here are people in the group. The two people that you saw on the first slide, Frank Arnold is now at the Max Planck Institute in Dresden, and Harriet is working for Oxford Instruments. So with that, I'd like to conclude.
We have time for one short question.
Thank you, John. That's pretty impressive. Of course, I'm going to ask about the superconductivity. Do you have evidence in any other materials about the nuclear mechanism for the pairing? Because it would be interesting, like even in the cuprates, where there's clearly phonons are involved, spins are involved, to see which, we're getting the feeling there's multiple mechanisms, a little bit of salt, a little bit of pepper, paprika.
Yeah, so I think we're not saying that the nuclei are key to the pairing. They are playing a role here. You see that there's a re-entrance of the superconducting transition. So that indicates that there's a temperature-dependent magnetism. And we believe then that that's coming from the coupling between the electronic spins and the nuclear spins. I mean, the thing about this phase diagram is that really that antiferromagnetic phase is really not very well understood. And I think the nature of this quantum critical point also needs more work to clarify it. But my point was that varying the isotope gives us a very nice tool to make things different in very, very clean materials. And the other point I'd like to say is that this transition and the nature of it, if it's intrinsic, this is in zero magnetic field. So this looks like a dissipative superconducting phase. So if it's dissipative, what's the source of dissipation? It's not field-induced vortices, but it may be something that arises from the intertwining of the magnetism and the superconductivity. It's sort of a bit like, you know, the SO5 idea. Yeah. But that needs more work to prove it. Thanks for the question.
Thank you again.